हाँ जी.
Good morning, student. As we all know that the whole world is suffering from coronavirus problem. So, Khalsa College take an initiative for online teaching so that your basic syllabus can be covered. As in earlier classes, we discuss about what is base space, null space, rank nullity. Now we will discuss about isomorphic vector spaces. We have in this problem we have discussed about theorem of on isomorphic vector spaces. To discuss this theorem, firstly we will discuss about 1-1 onto transformation. 1-1 transformation. Let T V to B W be a linear transformation. Then it is called 1-1 transformation for all x y belongs to B. If Tx is equal to B Ty, then x is equal to y, then T is called 1-1 transformation. Onto transformation, T is called onto. If and only for each B, W belongs to W, there exists one element B belongs to B such that B is equal to W is equal to T of B, or W is said to be range of B. Now non-singular transformation. T is said to be non-singular transformation if and only if null space of T is a zero space. We will discuss about what is null space. Image of each vector of B is a zero. If that means if TV is equal to 0, this implies B is equal to 0 for all B belongs to B. If it is not non-singular, then it is called singular transformation. That means there exists a non-zero vector whose image is 0. That means if B is not equal to 0, this implies T of B is equal to 0. Then it is called singular transformation. Now we will discuss about isomorphic vector space. Two vector spaces V and W over the same field are said to be isomorphic if and only if there exists a linear transformation V to W such that T is 1-1 and onto. If transformation is 1-1 and onto both, then V to W is isomorphic. Now our theorem is, that is on page 177, theorem number 24 of your book. Statement of theorem is that prove that two finite dimensional vector spaces over the same field are said to be isomorphic if and only if they have same dimension. That means we will prove that B is isomorphic to W if and only if dimension of both are equal. Firstly, we take B is isomorphic to W and we will prove dimension of B is equal to dimension of W. B is isomorphic to W. As we know, B is isomorphic to W if it is 1-1 and onto transformation. So it is given that there exists a linear transformation which is 1-1 and onto. We will prove dimension of B is equal to dimension of W. To prove this dimension of B is equal to dimension of W, we have to find a basis set of B and W both. Since B is a finite dimension, it is given B and W both are of finite dimension. If B is finite dimension, that means there exists a basis of finite number of elements. So it has a finite basis set. Let us take B1, which is equal to B1, B2, Bn. It is a basis of B. If it is a basis of B, then dimension of B is equal to n, because number of elements in the basis is n. Now, if this is a set, this set is a basis of B, and transformation is B to W, then T of B1 is an element of W, T of B2 is an element of W. That means this B2, which is a subset of W, and it has n elements. Now we want to prove that, we want to find the dimension of W. If we prove that B2 is a basis of W, then that means dimension of W is equal to n. To prove B2 is a basis of W, B2 is a basis of W, is a basis set. If we prove two results, firstly B2 is linearly independent, secondly linear span of B2 is equal to W. Firstly we will prove B2 is linearly independent. As we know that B2 is linearly independent when linear combination of vectors of B2 is equal to 0, and we prove that all the scalars are equal to 0. So take linear combination of vectors of B2 is equal to 0. If there is linear combination of 0, then we know that T is a linear transformation. So by definition of linear transformation, T of alpha V1, alpha V2 up to alpha Vn is equal to 0, and we also know T of 0 is equal to 0. So we can put here T of 0. T is given. It is given to be 1, 1. If T is 1, 1 mapping, that means we know that T of x is equal to T of y. This implies x is equal to y. This is the definition of 1 mode. So that alpha 1 v1, alpha 2 v2, alpha and vn is equal to 0. This is equal to 0, and we know that v1, v2, vn, these are bases of V. If it is a basis of V, that means this set is linearly independent. If it is linearly independent, linear combination is equal to 0, that means all scalars are equal to 0. So V2 is linearly independent because linear combination is equal to 0, and we prove that all scalars are equal to 0. Firstly, we will prove that V2 is linearly independent. Now, we have to prove to show that V2 spans W. V2 spans W, that means we have to show a linear span of V2 is equal to W. That means we have to show any element of W can be written as a linear combination of the vectors of V2. Say Y belongs to W, Y belongs to W, and T is a linear transformation from V to W. So there exists X belongs to V such that Y is equal to Tx. X is an element of W. If X is an element of V. If X is an element of V, then X can be written as a linear combination of the vectors of V. So X is equal to beta 1 v1, beta 2 v2 up to beta and vn. Y is equal to, here we have Y is equal to T of this, and now we take definition of transformation. We get beta 1 T of vn up to beta and T of vn. Now we get Y is a linear combination T of v1 up to T of vn. That means linear span of v2 is equal to W. Now, so we have proved that v2 is linearly independent and linear span of v2 is equal to W. That means we prove that v2 is a basis of W. If v2 is a basis of W, v2 have n elements. So dimension of W is equal to n. Dimension of V is also equal to n. Dimension of W is n. Both are equal. So we will prove that dimension of V is equal to dimension of W. First part is complete. Now we will prove conversely. In conversely, we will prove V is isomorphic to W, and given that dimension of V is equal to dimension of W. To prove V is isomorphic to W, we have to prove there exists a linear transformation which is 1, 1 and on 2. Firstly, we take what is given, dimension of V is equal to dimension of W. Say both are equal to n. If dimension of V is equal to n, that means there exists a basis set which has n elements. So take V1 is equal to V1, V2, Vn is a basis of V. Similarly, dimension of W is also equal to n. So take V2 is equal to W1, W2, Wn. This is a basis of W2. This is respectively. Now let V is an element of V. If V is an element of V and V1 is a basis of V, then as we know that definition of basis, V can be written as a linear combination of V1, V2, Vn. So write V is equal to alpha 1 V1, alpha 2 V2 up to alpha and Vn. We define here we define a mapping or linear transformation. So firstly we define a transformation. Transformation say T of V is equal to this and T of V is equal to alpha 1 W1 up to alpha and Wn. This is a transformation V to W. That means we define T of summation of alpha I ds is equal to alpha I ws. This mapping is defined by us. So firstly we have to prove that it is well defined mapping. To prove this well defined mapping, we take alpha 1, alpha 2, alpha and these are unique scalar. If these are unique scalar, then this linear combination are also unique. This is an element of W. If this is an element of W, alpha 1, W2, alpha and Wn is equal to T of V. So T of V is an unique element of W. This is an element of W for given vector V belongs to this V. That means T is a well-defined mapping. Firstly, now we will prove T is linear transformation. As we know that T plus beta of Ty. Now take xy, both are elements of B and alpha beta are scalars. If x is an element of B, then x can be written as a linear combination of the vectors of B. So summation of ai is bs. If y is an element of B, then y is also y can be written as a linear combination of b's. Beta is bs. Now we take left hand side, t of alpha x plus beta y. We put the value of x and y. Then we take transformation like this. T of summation of alpha I bi is equal to alpha I wi. Here we will get summation of alpha I ais plus beta is bi's and wi's. Now take alpha beta as common elements and we get T of alpha x plus beta, alpha of Tx plus beta of Ty. We prove T is a linear transformation. T, which we defined as earlier, T is well defined as well as linear transformation. Now we prove T is 1-1 mapping. To prove 1-1 mapping, as we know that we have to prove T of x is equal to T of y. If both are equal, then we will prove x is equal to y. Take Tx is equal to T of y. Put the value of x and y, both are equal. Take transformation as we defined above. The summation of a is wi's, b is wi's. Take this term on the left hand side, we get this term. And now wi's. Wi's is a basis. W1, W2 up to Wn is a basis of W. This is a basis of W. If this is a basis of W, that means this set is linearly independent. If this is linearly independent, that means all the scalars are equal to 0. Scalars are ai and bi. That means ai minus bi is equal to 0. If this is equal to 0, that means ai is equal to bi. Both are equal, that means summation of ai bi is equal to summation of bi bi. Both are equal to 0. Both are equal, that means x is equal to y. So T is 1-1 mapping. Now next we prove T is onto mapping. T is onto. Let W be an element of W. This is arbitrary element. If W belongs to W, then this W can be written as a linear combination of bases of W. And B2 is a basis of W. This B2 is a basis of W. So W is equal to C1 W1 up to Cn Wn. Let suppose that B is equal to C1 B2 C2 B2 up to Cn Bn. T of B is equal to, as we defined like this, T of B is equal to C1 W1 up to Cn Wn. This is equal to W, so we get T of B is equal to W. If both are equal, that means T is onto. So we proved here T is 1-1 onto. If we prove T is 1-1 and onto, that means B to W transformation is 1-1 and onto. Therefore, B is isomorphic to W. This is all about our theorem of isomorphic vector spaces. Both vector spaces are equal to, both are isomorphic if they are, this mapping is 1-1 and onto. Now we take an example of 1-1 and onto. Show that T is a transformation R3 to R3 defined by this is bijective. Bijective means 1-1 and onto both. Solution. Firstly, we will prove T is 1-1 mapping. 1-1 transformation. Let u is equal to x1 y1 z1, v is equal to x2 y2 z2, both two elements of R3. To prove 1-1, take T u is equal to T of v. We put the value of u and value of v. Take transformation as defined in the statement. T of x y z is equal to x lambda y z. So x1 lambda y1 z1. Similarly, on the right hand side, x2 lambda y2 z2. Both are equal, that means x1 is equal to x2, lambda y1 is equal to lambda y2, z1 is equal to z2. That means x1 y1 z1 is equal to x2 y2 z2. Both are equal. This is a value of u, this is of v, that means u is equal to v, that means T is a 1-1 mapping. Now we prove T is onto mapping. Now to prove T is onto transformation, let A, B, C belongs to R3 any element. T is onto if there exists x, y, z belongs to R3 such that T of x, y, z is equal to A, B, ABC. That means we have to prove their existent pre-image. So Txyz is equal to ABC if x lambda by z. We take this transformation x lambda by z is equal to ABC. Both are equal if x is equal to a, lambda y is equal to b, z is equal to c. That means x is equal to a, y is equal to lambda inverse b, z is equal to c. That means we prove that for a, b, c belongs to R3, there exists a vector x, y, z. X, y, z values of x, y, z are x is equal to a, y is equal to b by lambda, z is equal to c. This is an element of R3 such that T of x, y, z is equal to a, b, c. This is then we prove T is onto. That means T is 1, 1 and also onto. That means T is bijective mapping, which we have to prove. Now this is all about our theorem and one example. If you have